it is either going to be theta of 1 if r is less than 1, or it is going to be theta of r raised to the power of n if r is more than n. We can also have cases where our internal statement or internal equation that we are summing over depends on I itself. So in such cases, we have to remember this formula that it is usually n raised to the power of the power plus 1. Right. So here we have the summation of I squared for I1 to n. We have n cubed by 3, or that is in general theta of n cube. Generally, I raised to the power of k sums up to n to the power of k plus 1 by k plus 1. We also have cases where we have I times 2i, or 2 raised to the power of I. We already know that we can derive the value of 2 raised to the power of I. And then we are just multiplying the value of that for each step, the value of I itself. That usually tends to be n times 2 to the power of n. 1 over I goes to log n, and log of I goes to n log n, right? These are some important formulas that you might like to remember, but just keep it in mind. You can also derive it. I can also show you the derivation later at some point. But okay, so let's move on because we are still reviewing. We also have summation manipulation rules. So AI plus BI. Okay. We also have some more summation manipulation rules, such as AI plus BI can be broken down into AI plus BI. C, a constant times of AI, summation over I, can become C times summation of AI. And I from M to N of AI can also be rewritten as I from M to X, AI plus I of X plus 1 to N, summation of AI. Okay. For example, we have this particular equation, that is, we are trying to derive the solution to 4i plus 2 to the power of I, where I goes from 1 to n. Now, we have two terms here, right? 4i and 2 raised to the power of I. So 4i can be broken down into, so this entire equation can be broken down into two components, two summations, but the first summation can again be broken down using the constant part here, so 4 of I, so 4 of summation of I, and then I1 equals 1 to n, we have 2 raised to the power of I. So we know that I1 through n, 2 raised to the power of I is going to be 2n plus 1 minus 2. We just saw that. And for this particular thing, it is n squared plus n divided by 2 times 4, that becomes 2n times n plus 1. Okay. We also have this particular equation, that is n divided by 2 raised to the power of I, where I goes from 1 to n. N is a particular constant that does not depend on I, so we can take n out. And we say that for all I 1 to n, sum up 1 over 2i. So can someone tell me if this would approximate to n? Is this correct? Is this statement correct? That n times summation of 1 over 2i, I goes from 1 to n, will tend to n, or will be approximately equal to n. It is approximately equal to n because we are multiplying it, but we are still adding up a multiple set of series numbers, right? So it is a geometric, it is going to be n plus 2, exactly. Okay, so how do we know it is going to be n plus 2? Because in this particular case, half raised to the power of I, we can use the same formula as we did earlier, that is r raised to the power of I using the geometric series. And essentially we can apply that formula to figure out the summation of this internal sequence. We say it is approximately n, but more tighter bound would be that number is going to be n plus 2. Usually this is a very nice algorithm complexity when we are trying to find out. So when your computer allocates dynamic memory, right? So you have your RAM, some processes are using some part of your memory and sometimes they leave. And you can see, I'm sure that everyone knows what fragmentation of memory and defragmentation of memory is. So fragmentation of memory is when you have free memory in some slot, but that slot is not enough to accept or allocate a new program because the new program is much larger. So in such a scenario, you would need to find out an allocation algorithm that finds and allocates dynamic memory to your algorithm and maintain and shift out memory cells and so on. So this is an example complexity of such an algorithm. Okay. Then we also wanted to look into summation of I 1 through n log of I. So in this particular scenario, we have log 1 plus log 2 plus log 3 plus log 4 and so on all the way to log n. And if it is all the way to added up all the way to log n, we can rewrite this using our log equations as 1 times, 2 times, 3 times and so on all the way up to n. Right? That basically becomes n factorial. And we all saw that log of n factorial is going to be n log n, right? Because n factorial was decomposed using the Stirling's formula. That was n raised to the power of n plus half divided by e to the power of n. And that generally bounded it by n log n. This would be the time complexity if we used selection sort. I mean, this is the time complexity of many algorithms, but this particular formulation is if we had used selection sort using a priority queue of numbers that gives you a sorted order of numbers in a sense when you use a priority queue, and that you just push into the array over time. The complexity of selection sort would become n log n. Okay. I guess that's it for our review. Yes, yes, Matt, my computer is plugged in. Why? Can you not see me?
Yeah, I just saw a little icon in the bottom look like your battery was running out. Just want to make sure you didn't get cut off.
Oh, thank you. That potentially might be an email, but thanks so much.
Okay, cool.
That did happen once. Thank you.
Yes. The other question I had was the dominance rating. Where would you include the n log n to the dominance rating chart that you had?
So n log n would be somewhere that is
where does
obviously higher than n, but obviously lower than any exponent, any polynomial of n, right? So larger than n squared, smaller than n, because it is n log n, and it is also going to be much larger than log n itself.
Oh, actually, I see. I was looking for the n log n compared to the log of n factorial, but you're equating the two.
Yes, because both of them are going to be a similar complexity, because log of n factorial sort of becomes n raised to the power of n, and that basically becomes n log n.
I gotcha. Right? Thank you.
Thank you. Any other questions?
Not a question, but a statement. Mm-hmm. I feel it's very informative, and I feel like I'm following, but it's also somewhat confusing. And then when you went from the actual computer language to interpreting that into the equation,
yes,
I think it's going to be a little bit difficult or challenging.
Okay, I'm guessing you're going to talk, you mean this particular scenario, right?
Yes, yes.
Okay. So let's look into this particular. Yes.
It was just more of like a comment. I'm sure we're going to it'll start to click more as we get into the class.
Okay, so usually yes, it would be better as you get into the class more and you actually learn about the algorithms. Right now we are just recapping these things, but in general, when you have nested loops and those loops are in some order going to n, right? So I will explain this in a bit more detail, but if you have nested loops, you basically have a polynomial function for complexity. If you have two nested loops, just think about it in terms of n squared. Three nested loops gives you n cubed. But now look at the innermost nested loop in this for loop here. We have, so both of those two loops, k and I, go from 0 to n. Forget about this if condition for now. Both of those go from 0 to n, right? So we know that it is going to be n squared. But the internal loop goes from 0 to I, right? Where I is going to be 1, 2, 3, 4, all the way to n. In that situation, now let's just look at this internal loop, just that internal. Okay, and type it out, I mean in pseudocode. So we have for, let's say I goes from 0 to some number n. Internally, we have another loop for j that goes from 0 to, let's say I, right? So we know that the external loop is going to loop n times. So whatever we get for the internal loop, we need to multiply it n times, right? We have to do it n times. So the
Right.
internal loop, initially, let's say that the value of I is, let's start with 1. Let's not go with 0, but essentially initially it is going to run for one iteration. The next time it runs, I becomes 2. So it runs for 2 iterations, right? The next time it becomes 3. So it runs for 3 iterations, then 4, and so and so and so until I becomes n, where the internal loop runs for n iterations, right?
Right.
So essentially we are summing up all of these number of iterations together. And we know that sum of all these numbers is what? Sum of 1 plus 2 plus 3 plus 4 all the way to n.
You're saying the n factorial, is that what you're saying? Or
No. That is n factorial is 1 times, 2 times, 3 times, 4 times, and multiplicate.
Adding them all together, the sum of them, I forget what.
It is going to be n times n plus 1. Yes, exactly.
Okay.
You guys are there. Yes. So it is going to be n times n plus 1 by 2. And what is the simplification of this thing? That is n squared plus n by 2. So then what is the order of growth for this particular 2 nested loops? N squared.
Mm-hmm. That makes sense.
So if these two are n squared, then we can say that we have another n on top, that is the external most loop. Then we have n cubed. Where x less than 50 or x greater than 50 is just something that is important in the case of best case analysis. Where we have x less than 50, then it just takes n times, right?
Okay, that makes sense.
Okay, so on that note, I don't know if everybody heard. So everybody look at this particular function carefully. We know that the worst case is n cubed. What is the best case of this function? N, right? Best case would be, what is the condition for our best case? X is less than 50, exactly. Whenever we have an x that is less than 50, our best case comes up, that is big O of n, right? Or big omega of n. Yes. Perfect. Any other questions? Nope. Okay. So next class we are going to, so that's it for today, but do hold on for a second. Taha, no, see, best, oh, right, Taha is right. Yes, so it is not less than 50, my bad. Yaswanti, you're wrong, Taha is correct. It is going to be x greater than equal to 50. That is the case where this single print statement comes up. Yes, you're right. When we have x less than 50, that is the worst case scenario for our algorithm. Yep. Okay. So next class, we are going to look into divide and conquer algorithm. So for this class, we talked about different equations, and we also looked at polynomial equations, but mainly iterative complexity analysis, right? Where we had summations or products, where we had loops and things like that. And we were trying to analyze the complexity of a particular function or an algorithm based on these iterations of these equations. Next class, we are going to talk about divide and conquer approaches, where your equation is sort of has a recurrence relationship with your entire function. So something like your time complexity of T of n depends upon the time complexity of the